So they have the raw PDF documents, and they do some kind of PDF extraction, and now it becomes, messy, low quality, text documents, and then they segment those documents, they put them into the RAG, and then they use a large language model to handle user questions and answer questions for the user, right? But of course, this is a very primitive. There's no true understanding of the legal data. There's an over reliance on a base large language model, and there's no system of record. Nothing is in the database. There's no durable moat. Anyone can use large language model to do this and provide some low quality service, and they can be replaced by any other company in just a few weeks even, right? So that's.
Can you explain what the moat is? Probably the student don't understand what the moat is.
Yeah, moat is like a very frequently used word in the Silicon Valley, in the Bay Area, right? So originally the meaning is like the river across your city, like which protects the city from invasions. Like the ancient cities, there's always a water, a small river circling the city. But here, what it means is like something that can protect your business, right? You have something other people, it's very, very difficult for other people to build. Once you have that, your business is safe. It's not easily replicated by any other companies. But if it is a large language model wrapper, if your company is nothing more than a large language model wrapper, then it means anybody can replicate that, very, very easily, and you don't have a moat, right? So this is an important concept in the Silicon Valley, and when you build a startup, the first question you need to answer when you go to the investors is what is your moat? Okay. All right, let's go on. Since the first step is always paperwork and understanding those documents, so let's start with PDF understanding. How do we understand those PDF documents, right? So there are lots of companies that handle PDF documents, and some of them are already very, very important business. Like this Pulse is a company that handle receipts, right? All these costs and tables, and it can convert the thing on the left hand side, which is a PDF document, and on the right hand side, this is actually extracted from the PDF, but it's already structured data, right? But this actually can be quite complicated. Like this is a real receipt that I was in a restaurant in San Francisco, and I had a dinner, and there's a receipt, and if you look at that receipt, it says at the bottom add tips, right? I checked the first option, which is 18% of the tips, so the total amount is $88 dollars and 44 cents. And on the left hand side, you see it actually extracts $88 and 44 cents, right? So it knows, like it can understand the check mark, which is manually checked, right? So it's not that trivial. And this company is called Ramp. It's a very, very successful startup company right now, and a lot of companies are using Ramp to handle these receipts, and everything is automated. But things can get really, really complicated, and this is the PDF document that we have, and this is actually a police report, part of a police report. On the left hand side, if you look at it in the middle, it actually talks about the car, which part of the car was damaged or something like that. So as you can see on the right-hand side, and there are a lot of handwritten notes and check marks and all these kind of things. So understanding that is not easy. And this one is also similar. You see a lot of handwriting notes, but one thing I want to highlight is like there's also this image which shows the how the cars how did the collision happen, right? It draws all these cars that are moving, and then one car hits another car, and there's a third car, in the picture as well. And on the right-hand side, it actually has a textual description about what happened. Unit 1 and 2, they are traveling south on I-95, some kind of description. So these are the documents that we are handling, right? As I mentioned, there are already many startup companies just focusing on understanding these kind of PDF documents. There are platforms, there are APIs, there are domain specialists like companies handle receipts only. But this already just the PDF is already a very big space. There are many companies, but not all the problems have been solved at all, right? So let's go back to this picture where you have this raw PDF documents. You have a hand drawing picture showing how the cars get into some kind of collision accident, and if you use OCR software or use a large language model, you get all these kind of outputs, and you can use the visual large language model. It gives you a different type of outputs. So the first question here is, how do we evaluate their results? So there are so many different approaches: OCR, large language model, visual large language model, and for visual large language model, you have so many different solutions as well. And the new solutions are coming out every day, right? Almost like every day. So how do we evaluate? That's the first question we need to answer. So one thing we actually do is we use question answering based evaluation. So the challenge is, like, as I mentioned, many new solutions, in particular vision large language model like Gemini and the Cloud are becoming more and more promising, but new versions are coming out all the time, right? So, but every vision large language model or every OCR based solution, they give you different results, different format, different descriptions. So it's not very easy to just compare which one is better, right? So instead of just comparing raw text or output, we actually judge new technologies on how much they improve a model's ability to answer specific questions about a document, right? So we just use their output as input to some large language models, and we have a set of questions, and we ask the large language model these questions, and by giving after we give them this output from the PDF understanding documents, right? And we test on difficult representative pages that are critical for downstream tasks. And in this way, we decouple format from quality. So we don't care what kind of format do you use, whether you describe things in one way or the other, whether you use tables or whether you use narratives, or whether you use the bullet points or whatever you do. But we use your output as input to some large language model, and we ask the large language model to answer questions using your input. And if your input can enable the large language model to better answer the question, we might say, okay, this is a better approach, right? So this is how we do what we do. There are actually two approaches. One is golden extraction. We just created some synthetic question and answer data. Vision large language model extract the data from a document into some structured format. We manually refine this version, and we then generate. We then synthetically generate a question answering pairs based on this golden data set. And the strategy two is a little bit different. We extract data from the document, and we synthetically generate Q&A data set from the initial extraction. And we then have humans manually review and refine the Q&A pairs to create a golden data set. Not that much difference, but the idea is like, have a synthetic data set. And then, we also use vision large language models, this enable us to get the description of a figure, of an image, right? So previously I talked about this, how these two cars or three cars, get into this accident, how they collided each other, and this is an image, and the vision large language model will convert this image to a textual description, right? And then we can handle, give this textual description to the large language models, and the large language model will be able to answer the question, right? But here's a significant problem. We cannot really ask the vision large language model to answer a question anytime we have a question, right? Anytime we have a new question, we go to the vision large language model, ask the vision large language model to process the image again and answer the question for us. That is going to be not just very, very expensive, but also very, very slow. So what we would like to do is like, okay, can we have this vision large language model convert this image to the text in the most appropriate way, so that the text will contain enough information to answer the most likely questions people will ask for this type of images, right? What does that mean? So if you have two cars involved in a collision, right? The type of question may be some a newspaper or journalist ask are actually quite different from the type of the questions these lawyers or insurance company will ask. They are more concerned about not just how these cars get into this accident, but like whose responsibility it is, things like that, right? So it's the type of question, the focus that actually makes a difference. So how do we teach these vision large language models to describe those images in a way that the questions of interest will be answered in the best way, right? So we go one step further in this QA-driven summaries with reinforcement learning. So the core idea is that instead of showing the model the exact correct output of every document, we give it a goal and then automated the reward system, allowing it to learn the best strategy through trial and error. So what does that mean? Basically, this is a reinforcement learning situation. We are training a model, which we call the summarizer, to generate text-only summary that is very complete and relevant. And then, a separate AI can answer the detailed question about the original document using that summary. It's not going to go back to the image, right? And the test of success is like a high score on this QA set is an end-to-end validation of the summary. So, you know, if you get a high score for this QA set, that means you have a better summary. And this, you know, will be used as a reward function for this summarizer, right? And here is basically, you know, the workflow. So you have an image, and you have a question generator. This is a vision large language model. This is a frozen vision large language model, meaning like we are not change this vision large language model, right? This is fixed. And then the question generator generate a set of questions and ground truth answers, right? And then you have a question answering helper. It will be able to answer a question based on the summary generated by a vision large language model. This summarized large language model is producing this summary to be used as the input for the question answering large language model to answer the question, right? And then based on the answer of the question, because we know the ground truth, we can calculate or we can, you know, compute whether the answer is a good answer or not, and the result will be used as a reward in this PPO process to train this summarized large language model, right? So this is basically the process. We have a set of questions. These questions are legal related questions, and we want to use these questions. And since we know their answer, we want to use these questions and answers to train this summarizer. So after a lot of training, this summarizer will getting better and better to summarize an image into the best description, so that this description will be best can be best used to answer all these relevant questions. So this is what we are doing in understanding these PDF documents with images. And this slide basically just describe you know, what I just said in the previous slide. It's a reinforcement learning based solution to train a vision large language model to provide the best summary of the image. All right. Now, this is just the first step, understanding the PDF documents. There's a lot of other work that is needed to understand the documents. So how do we understand the documents, and how do we, you know, answer questions based using these documents, right? You know, I mentioned this slide, like previously you have a, you know, people have built this, you know, large language model wrapper to simply, you know, handle these chunks of text and answer these questions. Of course, this is really very primitive, and a lot of questions they cannot answer very well. And there are sophisticated solutions, for example, like this one. This is a recent paper by I forgot which university, but you can search for it. It's called MDoc Agent. It creates a much more sophisticated framework to answer this question. So this is like a much bigger jump, leap from that, you know, large language model wrapper based on the simple RAG, right? But we can take a look at what exactly it does. So it also segment these documents, like this is stage one, right? It segments this document into text and also images. And they put these text chunks and the image into this RAG. You know, you have, when a query comes in stage two, you know, you go to the RAG, and the RAG gives you a top K text segment and the top K image segments, right? And using these text and the image, you can answer the question, right? That's in stage two. But it does not stop there. it does not just give back these answers to the user and say that's the result. It goes through a more sophisticated step in stage 3. It looks at these top K results, and this large language model agent called a critical agent. It tries to ask some critical questions about the answer and the input. For example, if you say, what is the amount of this procedure, how much does this procedure cost, right? And then the critical agent might be saying, find the evidence that shows this amount of the cost is $3,000, right? And then given these critical question, it goes back to the RAG and to get a new set of top K text chunks and the top K images, and then it look at their answers and then use their answers to decide whether the previous answer is the right answer, right? So it has this self questioning, self criticizing, self correction loop to evaluate your results. Basically, it is a simple RAG plus a self-correction loop. That is one of the representative work in this space, right? So I'm not going to go through this slide again. I mostly described in the previous slide. You have retrieval step, you draft an initial answer, and then you have a critical agent. You have a second step to diving into these evidence, and then you finally have a summarizing agent, which combines the previous answer and then the new evidence and decide whether this is something right or wrong, right? So these are the results. But what are the weaknesses of this approach? What are the weaknesses of this RAG-based approach, right? Most of the RAG approach, the biggest weakness compared with database is that it cannot answer aggregate questions. So for example, what is the average payout across all claims? That is a very difficult question for the RAG to answer. Basically, it needs to retrieve every relevant page and then do the aggregation. That's very difficult for the RAG. RAG is more suitable for answer facts, that you can, the answer can be found in one single segment, like, the facts related question, right? But there are a lot of interesting aggregation based questions, and also analytical questions, like has the number of denials increased quarter over quarter, things like that. And in the legal space, a lot of questions we ask are actually very sophisticated analytics questions that is difficult for the RAG, right? So for example, which types of cases are most likely to go to trial versus settle early? There's no single page or segment from a single case that answers this question, right? And how does attorney workload correlate with case outcomes or delays? Are there outlier cases where similar facts led to very different outcomes, right? These are analytical questions that requires you to analyze a lot of data, to aggregate, to analyze, to aggregate again, and to get the final answer. So these are the very difficult questions. These systems, RAG-based system, that is harder to answer. And as I mentioned earlier on, we are also interested in taking causal actions in legal AI. The number one example is the so-called demand send optimization. So the goal is to maximize settlement value by choosing the best moment to send a demand, right? You always need to make a decision. Do we have enough evidence? Do we have enough results that this is the best time to send a demand? Because time is money. If you send the demand early, you get pay early, and if you get the pay early, that means literally time is money, right? But if you send early, you might miss some future expense, and you get not as high a payout as if you wait. So you always need to, make a decision like, should I wait or should I send it out, right? So this is just one of those, causal AI questions we need to be able to answer in the personal injury law space. And all these type of analytics, causal questions, and things like that really require us to have a very, very good understanding of the data. It's not something like the RAG can be used to answer these kind of questions. So that is why we're building this system at the Even Up to be able to answer all these kind of questions down the road, right? So at the bottom layer, this PDF extraction, and then we do a lot of information extraction. We're not satisfied by just putting these segments, images, or text into the RAG, but instead we want to extract structured data out of these documents, and we create this database or the knowledge base or the system of record. And then we have the system of record, which is the database, and the semi-structured data, which is in the RAG. And these two systems coming together are becoming our data platform. And on top of it, we build this agentic platform, and on top of it, we have this system of intelligence and a system of action to support automation and to make good decisions. So this is the system we are trying to build here. And the core of this system is actually the system of record. If we have the structured data, then it is relatively straightforward to build a system of intelligence and a system of action. So a lot of focus in this legal tech space is about how do we create this system of record, right? So I want to just spend a little bit more time on this. And the goal is actually quite simple. There are four aspects of the goal. We want high quality, or we want low cost, because we are using large language model, vision model very extensively. So cost is a big issue. And we also want to have scalability. That means we need to be able to handle very, very large cases. Could be 15,000 pages or could be 50,000 pages, right? And also we want coverage. Here, coverage means like, these documents may contain lots of different type of information, and we want to be able to extract all relevant information all together, instead of like doing it, for each specific type of information, we'll have to extract, this type of information again from the documents, right? So, immediately you can think of two extreme solutions. One is a monolithic large language model, assuming you have a schema that describes all the kind of information you want, and you have these massive documents. And assuming like you can just throw these two things to a large language model, and the large language model will miraculously output this system of record for you, like the entire database for you, right? Of course, today this is not possible. There's no large language model can take that much input in one shot and produce that result. Even if, for relatively smaller cases, like maybe just 50 pages, and somehow the large language model can take these 50 pages as a whole. The quality of extracting complex entity relationships from these 50 page document is still very, very limited. We won't get very good answers. Another extreme is like, oh, agentic platforms are really very, very hot right now. And people just assume, we can always create many, many sub-agents and, and we have a coordination agent or, orchestrator agent. And somehow they will figure out how to do this job in the right way, right? That is another extreme. But you also know, like majority of agent system actually fail. They really don't know how to do this kind of job in the right way, especially in a domain where we actually need very, very high accuracy and precision, right? So what are the solutions? We look at some solutions and we come up with three possible solutions. One is the RAG-based and summary-based and schema-based. The RAG-based is similar to the RAG we described before, but previously when we described the RAG, it is used for answering a question. And here we are using the RAG to do information extraction. So it's a little bit different, but it still has very, very low the performance is not so good. And the other one, the second one is summary based. It is designed to reduce the to avoid the problem of requiring a very, very big context window, right? So we can use summary-based solution. I'll give it a little bit more description in the next slide. And then the final one is the schema-based solution, which is we think the most possible or the most promising solution. So what is the RAG-based solution? The RAG-based solution is basically doing information retrieval as if it is question answering, right? So for example, if we want to, extract the bidding information from the documents, the RAG just says, give me all the bidding pages, right? And the RAG will produce all these bidding pages, and then, we just collect all these bidding pages, and we send these bidding pages to the large language model, and we ask the large language model to extract the information, and and we have the structured data. But the problem with this RAG-based approach is like, the RAG does not guarantee you that it will retrieve every relevant page for you, right? So if you are interested in bidding the total amount of a bill, RAG does not guarantee that it will give you every bidding page. It might miss some page. And if it misses one page, then of course your total bidding amount won't be right, right? So that is the biggest challenge here. And in order for you to not miss any relevant page, you have to make your threshold very, very low so that it's possible for you to get all the relevant pages. But if you use a very, very low threshold, it means you won't be able to handle very, very big, cases of very, very big documents because, the RAG won't be able to return you all the relevant pages. So with all these problems, this RAG-based using question answering approach for information extraction is not really a very good approach. And the RAG is much better suited for question answering tasks rather than document understanding. Now, the summary-based approach is like, a compromise because of this, but it actually represents a big, leap in document processing. Instead of using RAG to return you a random set of pages, it is like reading a book, from the first page to the last page. So it's not going to miss any pages. So by definition, it will have a higher recall. And as it reads all these pages, it converts each segment into textual summaries. And then it sends those summaries to the large language model and to do the final extraction. And the one problem is like if the document is very, very big, and you can imagine the total amount of segments, the total amount of summaries are also going to be very, very big and won't fit in a textual window, context window. But there are ways to deal with this, like you can do, these rolling summaries or hierarchical summaries. But of course, these kind of things also come with a cost because there might be potential information dilution and information loss in this multi-step aggregation, right? And this comes to another very important observation in all these, pipelines and agentic systems in processing this information. We have all these sub-agents working together, and these large language model agents are basically taking text as input, and they communicate with each other in text. Which sounds nice, but there's a very big problem because the text are ambiguous, they are inconsistent, they are non-deterministic, and they usually will have lots of problems, not to mention, latency and other things, and very, very difficult to debug and all things like that. A better thing to do is like, instead of using this text, we want to use structured data in communicating among these agents. When you use structured data, everything becomes more precise and everything becomes more debuggable, and everything becomes more scalable. So that's just one very important observation in dealing with this agentic system. And this is also the foundation of our schema-based solution, right? So the schema-based solution takes three types of input. One is, of course, this document. The second is a global schema, which describes everything you want to extract from these documents. And the schema also comes with a lot of annotations, which are descriptions of entities and relationships, which are examples and which include constraints. So these kind of annotations will help us create agents to do the extraction, and the output is a structured data set. So how do we do that? First we decompose these schemas into smaller snippets, right? We call schema snippets. And then, these schemas, comes with annotation and the examples and everything. So we can automatically instantiate agents to do the extraction for any particular schema snippet, right? And on the document side, we also do segmentation. We cut those documents into, smaller pieces, but they are semantically coherent segments, right? And then we classify, we map each document segment to the snippets. It can be mapped to 0, 1, or multiple schema snippet. And once it is mapped into the snippets, we can invoke the agents associated with these snippets to do the information extraction, right? And this step is also automated. And finally, we have all these kind of information from these snippets, and we assemble them together, we stitch them together. That is the entire workflow. Of course, when you have a large schema and when you try to stitch things together, one very important thing is the entity and the identities of these entities. So entity linking is a very, very important step for this information extraction process. And in our system, the entity linking happens in two steps. One is the local entity linking, which is on every segment. And then there's global entity linking. We use global information across multiple segments to, disambiguate, to reconcile these mentions on different segments and to get the final entities, and we combine these things together, right? So this is the algorithm. And I have mentioned quite a few components: decomposition, segmentation, classification, entity linking, and stitching everything back together. These are the steps. But the devil is in the detail. I don't have enough time, but I want to just mention one thing. We talk about the schema decomposition, which means we, divide this global schema into smaller pieces, and then in every local document segment, we extract information from that document to that particular schema snippet. However, the global relational schema is designed according to the database normalization principle, right? Why do we design a database using these normalization principle? Because if we design the database based on these principles, it is good for storing the data, to retrieve the data, to update the data. If the data is not normalized, the schema is not normalized, as you can see, as you learn in your first class of database management, you will have a lot of update anomalies and things like that. However, when we do information extraction, we'll realize, okay, this schema is not really optimized for information extraction, because when you do information extraction, there's this locality. Relevant things are discussed together. And this locality of the information in a document do not align with the locality of the global schema, right? So there's a misalignment here. And I can give you two examples. One is a student enrollment. You have a student table, you have a course table, you have in the middle an enrollment relationship, right? And this is how your database is designed. This is the schema, in your global database. But apparently, this does not align with how information is organized in a textual document. When this textual document is talking about some student is enrolled in some class, it does not talk about things in these three separate things, right? And another example is medical documents, like assuming you have a procedure. There's a medical procedure, and this medical procedure is recommended by one medical service provider, one doctor, on a particular date. And then later on, maybe after 3 months, after half a year, this procedure was actually performed by another doctor on another date, right? And in your schema, you have this record which talks about the procedure and recommended by Dr. A and then later on performed by Dr. B. But in your documents, these two things will be talked about in two different medical documents separated by 3 months or 6 months. They are not together in one segment, right? So how do we, align this information in the documents with the global schema? That's the question. And what we do is, like, instead of doing schema decomposition, we are doing schema assembly. The question we ask is, how do we design schema snippets aligned with how information naturally appears in documents, while still allowing those snippets to be systematically assembled into the normalized global schema in the final stage, right? So it's a local schema design problem, which still need to maintain the completeness of the information. That's one of the detail, and also quite a big challenge in our system. That's all I have. There's a lot of related work, and it's still in the early stage. I still cannot talk much about experiments and the results. but I hope I give you like some a glimpse of both the problems and the challenges and some early solutions. Thank you very much.
Well, thank you, Bishon. This is great, a great talk. Normally we get this presentation on the completed research, but this is you're sharing the problem that you want to solve, and this is great because some of the student or faculty can do some technical work and communicate with you.
Yeah.
Any questions? I saw the Professor Huang was here, but I don't know whether she's
Hi.
still around.
Oh,
Hi,
hi.
Shin. Hi, good to
Yeah,
see you.
long time.
Yeah, wish the best for your new journey and even up. I have another meeting in 3 minutes, but I have a quick question. So I think your system depends a lot on the quality of QA. And do you have any comment on how we can collect useful QA? And another question is there a feedback loop for if there is any log for actual lawyer use? Can it feedback the system?
Yes. Let me answer your second question first. We have this thing called the case companion. It's sort of like uh, code writing code like a code companion, but it's a case companion where we interact. The lawyers interact with our system. They just ask all kinds of questions, and they will tell us, oh, this looks great, this is not right, and all things like that. So this creates some kind of data set for us. It's still not a completely automated correction loop, but it's some of our useful data for us to understand how our system perform. And your first question about the QA, so we do have like the real question and answer, the case companion data set, but we also in evaluating our system, we create a lot of synthetic data, as I described, like in the PDF extraction. But in many later stage, we have this synthetic data, using synthetic data to understand whether our system is doing good job. And in the last part, I presented this information extraction system. It also has a self-correction loop because when you try to stitch all these kind of things together, you will find discrepancies or things that it's just hard to stitch together, or they violate some kind of constraints you have, and then we'll go back and retrieve the relevant segments of these documents and ask large language model, okay, I have this particular problem, things do not come together, can you take a look, and what's the real how do we solve this problem? So there's a correction loop.
Thank you so much. I'll ask more offline. Thank you.
Okay, thank you, Professor Wang, for asking question. The student can ask questions, but in the meantime, Professor Liu, you turned on the slide, the screen.
Yes, thanks for very insightful talks. I think I learned a lot. Following up previous question, in the legal domain, can you somehow assemble a set of good questions by contacting lawyers? So in specific case, ask typical lawyers, would you please raise some interesting questions regarding this case? And then by going over such processes over and over again, if we can come up with some good pool of domain-specific questions, then I think your refinement will work better, I think. So how do you think about that?
Yes, that is a very good question. We do work with lawyers very closely. Currently, even App has 2,000 legal firms as our customers as our customer. So we work with them very, very closely. They give us lots of feedback, and our goal is just to, make sure all of their questions are, very well answered with high quality. There's still a lot of room for us to improve. But there's one more thing I want to mention. They ask questions, but they don't know what are the potential questions they may be able to ask. Because as I mentioned, this space has never been automated before. So the data has never been in a database before. It's always on PDF documents. And if you want to ask questions, they ask those paralegal people and they go and read these documents for you. So apparently a lot of hard questions are, not answerable in this, very, very rudimentary approach. And now if the data is in the database, then you can answer, they can actually ask a lot of sophisticated questions to compare things across the board and all these kind of things. So they are also learning, the potential capabilities of, this type of solution, like the system of work solution. So this will, up level, this legal domain quite significantly.
Thank you. And I'll just ask one more question quickly. You compared approach 1 versus approach 2. So approach 1 is like one fits all, but in fact, it cannot fit all. So you recommend approach 2. Approach 2 is basically divide and conquer and mix and match. So by using snippets, you are dividing the whole task into subtasks. And then by stitching, you are assembling relevant parts. So the whole quality of your procedure will depend on how to divide and how to assemble. So the quality of snippets and the stitching techniques. How do you think about that?
Yes. So, as I mentioned, the devil is in the detail. It's, it is quite easy to, either, decompose the big schema or what I described, or, how do we, do things in the other way, create sub-schemas and ensure all these sub-schemas can be assembled into a big schema. But the challenge is in, like, the information is really, really distributed very, very unevenly across all these kind of information, all these kind of documents, right? Some kind of, provider information or, plaintiff information is on many, many pages. And you can imagine, like, for example, one legal case involves several, plaintiffs, right? And not every page or every segment mention this plaintiff's name, but it is only available through the context. However, when you extract information from a particular segment, you definitely need to know which plaintiff this information is about. So this means, like, just like you are reading your book, you need to remember things like in the early part of the book that you have read, not just only the information on this current chapter, right? So that is why a lot of details we need to take care of, like how do you remember things as you process things page by page.
Thank you.
So I imagine you use a lot of graph structures behind the scene.
We mostly use just a database and structured data, like we store the data in JSON files and and then in the relational database. At this moment, we don't use a graph structure that much yet. On the other hand, we are also building knowledge base and the knowledge graphs out of this data, and there will be graph data involved. Especially, we are also constructing this very interesting data set called the referral patterns. So one doctor might refer another doctor and things like that. This naturally creates a graph, and there's very interesting information out of these graphs.
So when you say schema, the schema. Aside from the schema that you mentioned so far, you also plan to build the graph and based on knowledge base, which will be more entity and relationship oriented, right?
Yeah. So the when it comes to extraction, information extraction, it's mostly about the relational database. But once we have the relational database, we want to do more analytics and all other things, and then we will create some kind of graph structure.
So regarding this knowledge base, I in recent discussion with one of the guys that I met in Seattle, so there seems to be a language that allows to express a first order and the second order logic. So I talked about the verification with you, when I was in Seattle, right? Yeah. So and so I don't know whether that kind of I think it's certainly the graph structure is limited, as you cannot express the first order logic. They cannot put the quantifiers in, right? Yeah.
Yeah. So we haven't considered these more sophisticated, like symbolic based solutions yet. Everything is still quite empirical at this moment.
Yeah. So I think I like your architecture, overall architecture. You need to have a systems of record, to be precise, and in fact, the good enough is not good enough. It also applies to other critical domains that are in interest, like manufacturing, and you cannot control the the plant with the input that good enough. You need to have a really precise input, to control.
Yeah. Totally.
Yeah. Well, thank you. Thank you very much for your sharing of ideas on the problem that you want to solve, and that's I like to keep in touch. Yeah.
Let's talk more. Thank you very much.
Yeah. Thank you.
Inviting me.
Thank you.
Yeah. Thank you. Thank you, Haisheng. Yeah.
Bye-bye.
Bye-bye.